This is the beginning of Chapter 8. We have just finished up talking about mole conversions and stoichiometry, and most of the time it's simply been dealing with a solid material. Well, in actual practice, chemists typically do reactions in solution, and so instead of just simply dealing with mole, they usually deal with a concentration, the most common of which for chemists is molarity. Molarity is defined as, I'm going to write it in formula, moles divided by liter. And of course, as all formulas, you need to be able to rearrange this formula to solve for anything. So if you want to solve for moles, of course, you're going to multiply both sides by liters, right? And if you want to solve for liters, you need to rearrange it. For those of you who struggle somewhat with algebra, here's one of the kind of easy triangles that helps you remember how to rearrange an equation. So if you use this triangle, just make sure that you have moles on top. It doesn't matter the order of the variables that you have on bottom, but whatever you are trying to solve for, you cover up. So let's say we're trying to solve for liters. We would cover that up, and the triangle would then tell us that liters is equal to moles divided by molarity. Molarity is quite simple to work with. I'm going to give you a couple of sample problems so that you can see the different ways it is worded and the different variables you're asked to solve for. This is a real straightforward. Calculate the molarity. Okay, you are given mass and volume. So let me redo this triangle up here with the symbols. Again, you want to have moles on top and molarity and volume, which needs to be in liters for this formula, on the bottom. Notice that mass, or grams, does not show up in this equation, right? So what are you supposed to do? Well, what variable in this equation can you get from grams? And hopefully you realize that's mole, right? You can get moles by dividing mass by molar mass. So let's do that. 34.6 grams, it's sodium chloride. The molar mass of sodium chloride, 58.44. And grams cancels, and we get moles from that. 0.592 moles of NaCl. All right, so now we can begin plugging into the formula for molarity. Moles goes on top here, so it's 0.0592. Liters goes in the bottom. Notice that the volume was given to us in milliliters. It needs to be in liters to use this formula. So just a quick reminder how to convert from milliliters to liters. There are 1,000 milliliters in 1 liter. So 125 milliliters equals 0.125 liter. So that goes on the bottom. Now, since we're doing calculations, I want you to start paying attention to sig figs again. Notice that all of the given information has 3 sig figs, so our answer should be expressed also with 3 sig figs, and here it is. 4.74 molarity. It is, as far as units, you can either express it with a capital M for molarity, or you can kind of write out what molarity stands for, which is moles per liter. Each is perfectly fine. All right, another example. This time the problem is asking you for moles. So let me put the formula up here again. So you either rearrange this formula to solve for moles, okay, and that moles would equal molarity times liters, or if the triangle helps you, okay, you're solving for moles, which means you cover that up, and that tells you right there that that's molarity times liters. So let's go ahead and fill in the information that were given to us. Okay, molarity is 0.254. I'm just going to write out what that stands for, right? Molarity is moles per liter. Liters again, and most of the time you're going to be getting milliliters time instead of liters, right? So again, we have to divide by 1,000 to get liters, or that's the same thing as moving the decimal 3 places to the left. So times 0.1 liter. And so our answer here is 0.0245 moles. Pretty easy, huh? And there it is, a little bit neater. Third example. This time it's asking for grams, and that's probably the most useful conversion to do as far as a chemist goes, because that's what chemists work with in the lab. They measure out grams when they're getting ready to do a reaction. So just associate grams and moles together, right? If you have grams, it's easy to get moles, or vice versa. So since grams doesn't show up in the equation, we know we're trying to solve for moles again, right? First, at least. And we know from the equation that if we rearrange it, moles equals molarity times liters. So let's get moles first. The molarity given to us is 0.50. And 100 milliliters, we divide by 1,000, or move the decimal over 3 places to get liters. All right, now, as far as paying attention to sig figs, notice that you only have 2 sig figs in the molarity value, although you have 4 in the volume. But the limiting factor, the one with the least number of sig figs, is going to dominate how many sig figs your product have. So we're going to express our mole with 2 sig figs. And because the problem asks for grams, we have to do one more step here. We've got to convert the moles to grams. The molar mass of sodium hydroxide happens to be precisely 40 grams per mole. And our answer is 20 grams of sodium hydroxide, which I did not express with the correct number of sig figs. I need to now write that with 2 sig figs. Right? Okie doke. So those are pretty simple. This is a little bit trickier. Hopefully you remember that ionic compounds, when they dissolve in water, the first thing they do is dissociate into the individual cation and anion. And you may remember that we talked about solvation, where they separate like this because they're stabilized by water molecules, which kind of build a cage around them and solvate them. It's called solvation, right? So, but in any case, if you look at the stoichiometry of this dissociation of an ionic compound dissolving in water, you notice for every 1 sodium chloride that dissolves, we get 1 sodium cation and 1 chloride anion. But that's not always going to be the case. Okay, let's look at the bottom. If we have 1 iron 3 perchlorate, it dissociates into 1 iron. See, there's only 1 iron atom in here. But we get 3 perchlorate ions. Okay? So an easy way to kind of remember that with an ionic compound that dissolves in water is the subscripts become coefficients, right? This subscript is simply telling us there are 3 of these anions in the compound. So we have to maintain conservation of mass, right? We're going to get 3. Why is that important? Because sometimes it's of interest, which means you'll be asked a question that says, if I start with 1 molar solution of iron 3 perchlorate, what is the molarity of perchlorate ion going to be once it dissolves? And the answer would be 3 molar. All right, so let me give you another example just to kind of make sure you understand the concept. Let's say magnesium chloride. Let's say that I massed out enough magnesium chloride to make a 1.5 molar solution of it when it dissolves. And when it dissolves, so you need to be able to write out the balanced reaction. It's not really a reaction, but dissociation of an ionic compound that dissolves. So this is, you have to go back and remember the charges, the common ion charges. And then you have to make sure it's balanced, right? This subscript 2 means there are 2 chloride ions that are going to be in the solution. So if I asked you, what is the concentration of chloride ion and what is the concentration of magnesium ion in this solution once it dissolves? Your answer would be 1.5 molar in magnesium ion because there's 1:1 there, and 3.0 molar in chloride ion because the ratio there is 1:2. If it makes more sense to you to write out kind of a unit conversion, you can do that. You could do, for example, 1.5 magnesium chloride times, for every 1 magnesium chloride, there are 2 chloride ions formed, all right? And so that means there are 3.0 chloride ions, okay? So that if you need to do it with unit conversion, that's the way you would do it. All right, just a couple more slides. It's still working with molarity. It's very common for chemists to make a concentrated solution of something that they're going to take little bits of on some type of regular basis. And so they call those stock solutions. And basically, you're going to take a little bit out of the concentrated stock solution and you're going to add more water to it. So you're going to have a diluted solution. And so I want you to be able to do calculations for dilutions also. The one thing that you need to realize in this case is that if you have a concentrated solution, so you have, I'm just going to draw like little particles. Okay, so if we could see on a molecular level, it would be, okay, so we'll call that concentrated. And then let's say that you pull out of there just a couple of those, just a little bit. Take a pipette, and we're going to say we removed 4 moles, 4 particles, okay? And then we fill it up with water. Okay. So the number of moles that you're talking about that you pulled out, let me get a different color pen, does not change when you add more water, right? So the moles doesn't change. The molarity is going to change because you've added more water, more volume. But the moles that you pulled out of the concentrated solution are going to remain the same. I'm telling you that because I want to show you the formula now and explain what it means. Here's the dilution formula, and you will use that a lot in lab if you haven't already. Simply what that says is the molarity of the concentrated solution times the volume that you took out of that concentrated solution equals the molarity of the dilute solution times the volume of the dilute solution. Where did that come from? What is that even saying? Do you remember what molarity times volume equals? Okay, remember that molarity is moles per liter, right? So if we multiply that by volume, okay, so molarity times volume is simply moles, isn't it? So what we're saying is the moles that we pulled out of the concentrated solution equals the moles in the dilute solution, right? So moles hasn't changed. So that's where the dilution formula comes from. And honestly, the only thing that's slightly tricky when you're doing a dilution problem is to make sure that you keep the pairs together. Okay, you're typically going to be given 2 different molarities or 2 different volumes, and you've got to make sure you match the right volume up with the right molarity. This is a visual example first, just because sometimes it's easier to see what's going on. So let's say that over here, which they probably should have shown and they didn't. Let's say we've got our stock solution over here. And by the way, I'm a horrible drawer, but these are called volumetric flasks. And they are precision hand-blown pieces of glassware that cost like over $100 a piece. But you should know the name, okay? Volumetric flask. And anytime a chemist is making a certain concentration of solution where the precision matters at all, they're going to use a volumetric flask. It is not precise to use a graduated cylinder, or certainly not a beaker. So let's say that over here we had a volumetric flask with a concentrated solution. So, and let's say we want to dilute it. So we're going to get it, we're going to pour out however much, usually with something more precise like a pipette, but we're going to decide how much of this concentrated solution we want based on how many moles we want. And so in this case, what they told us is that the concentrated solution was 10 molar. That is really concentrated, okay? So that's M1, if you remember the formula, right? V1, they're telling us that they measured out 150 milliliters, okay, which is the same thing as 0.150 liters, right? And they poured it into a new volumetric flask and then filled up the rest of the way with water. So to look at this from the dilution formula, M1V1 equals M2V2, again, M1 would be the original concentration of the stock solution, 10 molar. V1 is how much of that stock solution you used. In this case, they told us they used 150 milliliters, or 0.150 liter. And the flask that they put it into to dilute is a 3-liter volumetric flask. And from all that, they made 0.5 molar. So we started with 10 molar and ended up with 0.5 molar. So it was diluted by quite a lot. But again, mole equals mole. That's all the dilution formula tells us, is that the moles we took out of the concentrated solution don't change. So here's an example for you. I don't think it's going to be hard, so give it a shot first by turning off the video and then come back. So here is the dilution formula. Read it carefully because sometimes the wording can be a little tricky. I actually go through these dilution problems and I'll label these, like find the most concentrated solution, that's going to be your stock solution, and call that M1. So I go through each of the given information and label what it is in this formula. So when you think you have it worked out, turn the video back on and I will show you how to do it. All right, I hope you gave it a try yourself. So as I said a minute ago, the more concentrated solution, the stock solution, I call M1. Actually, it really doesn't matter if you call it M2. I mean, you're going to get the right answer. Just keep the right volume with the right molarity. The problem is asking what volume of that concentrated solution should we use. So we're trying to solve for V1. We don't know, okay? So this is what we're trying to solve for. What we want ultimately is 0.155 molar. So that is M2. Okay, that's the diluted concentration we want. How much of the diluted solution do we want? I managed to cover it up there. There we go. We want 10 liters. All right, so that is of the diluted solution. So that is V2. All right, so now we have all the information but V1. And so we're going to solve for V1. That just means rearranging the equation. All right, so V1, we're going to divide both sides by M1, right? So equals V2 times M2. Here, let me do it up here. V1 equals V2 times M2 divided by M1. And plugging in those values, we see that we need to withdraw 1.03 liters of the original concentrated solution. One thing that's really cool about the dilution formula is even though in the examples I've shown you, I used units that are typical for the molarity formula. In other words, I used liters. It doesn't really matter. If a problem, instead of giving you liters, gives you milliliters, like instead of 10 liters, they said, okay, 10,000 milliliters, you can use that milliliters in the dilution formula. You don't have to convert it back to liters because, as you can see, hopefully, the units will cancel. So let me just show you down at the bottom here. Let's see, the molarity of what we wanted was 0.155, right? So instead of liters, if I put milliliters here, doesn't matter because the milliliters, whatever the units are for volume, are going to cancel, all right? So just be aware that whatever units you use for volume on one side, those are the units you're going to get on the other side. So if we use milliliters over here, our answer is going to come out in milliliters. So just be aware of that. Here are 3 more practice ones, and I'm not going to work these out for you. I want you to pay special attention to the last 2. The first one's real straightforward. Look how similar the last 2 problems are. So read them over a couple times until you think you understand what the difference is between those 2. Because that's a tricky type of wording that I've seen often on standardized test questions, and you need to understand the difference, okay? So if you're in Dr. Maffei's class, these questions will be on Go Formative for you to answer.